Good afternoon, everybody, and welcome to this section of UCT's Open Day. This is electrical engineering. My name is Fred Nicholls. I'm the head of Department of Electrical Engineering. I'll start a presentation shortly, but just to inform everybody, there is a question and answer section in this forum. And I do have some assistants that are helping with that. So should you need any information, please feel free to post questions there and we'll try and answer them when we can. I'm hoping that my presentation is being shared. Can anybody confirm that?
All good.
Thank you. All right, so a quick look at the next 30 minutes. I will give an introduction, perhaps for about 15 minutes or so, just giving some details and some insight into what electrical engineering is, what electrical engineers do and the like. And then I've got a short show reel that we prepared for last year's Open Day. It's a bit sad that this year's a virtual Open Day again. It's quite nice seeing our prospective students face to face, but I guess this way we also get a chance to have bigger reach out further for people that can't be in Cape Town. But we've got a show reel from last year that we used that I'll show you a little bit of the facilities that we have on the campus available for our students. And then we'll wrap it up perhaps with just going through some of the questions that are being asked by the audience. And we'll see if we can assist you and guide you in that. All right, so the things I want to really discuss are what is electrical engineering? What do electrical engineers do? What is the typical kind of work or kind of job environment that an electrical engineer operates in? And what are the skills or the attributes that electrical engineers need to have? And ideally, which we as a university would try and instill upon our graduates. The types of things that electrical engineers need to be good at in order to excel at their jobs. And then, as I said, we will give you some insight into what the department looks like and how it functions. Right, so what is electrical engineering? I will say that there's some quite nice YouTube videos out there that deal specifically about what is electrical engineering, what is mechanical engineering, and I found them very useful as well. So I don't think I've got a link to them here, but if you search, you will find them, and they're very informative and quite accessible. But traditionally, electrical engineering is the study and the application of electricity, electromagnetism, and electronics. Now, the advent or the dawn of electrical engineering, I would say, probably was in the mid to late 1800s. So I'm just showing some of the origins of the discipline, as it were. Now, quite a lot of the origins are related to Nikola Tesla, who was an innovator and an experimenter and quite a colorful character. Who was operating towards the end of the 1800s, and he was trying very hard to understand the nature of electricity and what it was and what it could do, but particularly from a point of view of harnessing it and making it available for applications. So right on the left is a picture. It's actually a composite. It's a cheating photograph. But he had lots of resources and he had lots of funding. So the picture at the bottom is Wardenclyffe Tower, which he built towers to try and explore the capabilities of electromagnetic radiation. So that tower was actually, I think he was developing it primarily to try and do communications, but also to try and distribute, to broadcast energy, broadcast electricity, wireless energy. So we're talking about large million-volt systems, and the sparks that we're seeing on the left-hand side that he's presumably not really sitting in the room with. I think when the device got turned on and off, it made 7 or 8 meter long sparks that sort of look really good when you make it into a photograph and you go to an investor asking for money. One of the other things that he also encountered through his journeys was X-ray radiation. He didn't invent X-rays as an imaging modality, but certainly he encountered them inadvertently, if I recall. He had some photographic film somewhere and it sort of made images that he didn't really understand where they were coming from. And it turned out that he was generating X-ray radiation and it was interfering with photographic films. So the pictures that we see in medical sort of environments, X-ray and tomography scans and those kinds of things, they all come from electromagnetic radiation, which is essentially just the spectrum of light. Light that you can see and light that you can't see. On the top there, I've shown a photograph. I think it's a it's a replica, or it might actually be the original, of one of Thomas Edison's first light bulbs. That was also the advent of electrical engineering, was primarily to try and bring lights into the cities. So before electricity existed, the cities were lit by gas lighting, and when carrying gas around a city is probably quite a dangerous thing to do, seeing as it ignites and it's flammable and all the rest. But Edison and Tesla were both fairly competitive. They were working against one another, trying to win the race of making light bulbs that could light the cities of the time. At the bottom, I show a spark gap transmitter. Essentially, James Clerk Maxwell discovered through theoretical means that electromagnetic radiation should exist. And Heinrich Hertz actually built the first spark gap transmitter. Essentially, when you accelerate electrical charges or electrically charged particles, they generate electromagnetic radiation. And a spark is just a moving charge, so it radiates outwards and you can pick it up from a distance. So that's essentially the origin of Morse code and Samuel Morse's coding techniques for communicating over long distances wirelessly. And then finally, on the right-hand side is the replica of the first transistor. So that happened in about the 1950s, that Bell Labs was working on trying to improve valves and tubes, and essentially they discovered that you could do switching using semiconductor technologies, and that essentially was the start of the semiconductor revolution and I suppose all the devices that we see in front of us today. All right, so that's the traditional view of it. The modern view of electrical engineering is slightly different, but we're dealing, one of the primary drivers is power. We need to electrify our environments and our cities, and in order to do that, clearly we need to generate power on a large scale. Traditionally, things are coal-burning power stations, nuclear power stations, but nowadays, obviously, I think everyone's aware we're moving towards renewables, other technologies that essentially don't have a limited lifespan like fossil fuels invariably will have. So the whole idea of power, I think in South Africa at least, is going to be probably one of the most important topics for the next 10 or 15 years until we resolve our energy crisis. And our graduates presumably will be the people that will be well positioned to lead that revolution, so to speak. Control, one of the first control systems that I'm aware of, I think, was the Governor on James Watt's steam engine, but subsequently to that, I think it was Maxwell as well, also developed the fundamentals of feedback control. So control is basically working out how to actuate a system so that it does what you want it to do while you're measuring it and all the rest of it. And electrical engineers are very sort of conversant with that kind of technology. I've mentioned electronics. Microelectronics is another version of that. The smaller you make electronic devices, the more efficient they get, the less energy they use, and the faster they can switch. So the drive towards miniaturization of electronics is paramount. And obviously, electrical engineering people, knowledgeable in the area are instrumental in that. I guess in the future, we might not have electronic systems based on semiconductors and silicon. We might move into entirely different technologies like optical switching, and chances are that electrical engineers are going to have the skills to transfer into those new domains for the future. Then there's signal processing. The world is full of information. We can sample lots and lots of processes and get loads of data, but turning it into information is a signal processing endeavor. So how do you look at huge amounts of data and actually get the useful things out of it? How do you modify the representation to suit your purposes? That's a signal processing problem. And telecommunications, I think I'll talk a little bit about that later. Instrumentation is the process of measuring things. Electrical engineers do all of that kind of thing on plants, in other environments, all around. And then computers. We work intimately with computers. We can build computers, we can program computers, and we can understand computers. So it's a very important sort of component of electrical engineering. And then finally, we do have a mechatronics program in our department. That's a hybrid between mechanical engineering and electronics, essentially. So it's an interdisciplinary field. The world is a complicated place these days, and quite often you need people that span disciplines, and mechatronics essentially is the one program that we offer that it's sort of in the direction of robotics and automation and making systems that are intelligent, or mechanical systems that sort of have the electronic intelligence behind them. Right, what do you do as an electrical engineer? Well, primarily, I guess most people's jobs day to day would involve designing, developing, testing, manufacturing, say electrical equipment and systems, but not just electrical. The skills that engineers in general have are very transferable and very generic in some respects. And I guess it's the problem-solving elements that we really try and instill in our students, and it's the problem-solving elements that actually make good engineers. And they're not really discipline-specific. So the foundations of electrical engineering are obviously in electrical equipment and systems, but our graduates are very mobile and they can move into other areas without too much difficulty. I've got a couple of, I think I'll come back to that, but I've got a couple of examples of places or technologies that electrical engineering people work with, or instances thereof. And the one is the sort of modern day technologies. On the left here, you see a 5G cell tower. And essentially that's related to the Internet of Things. The idea is basically to have massively interconnected, large-scale systems. So lots of little devices that can talk to one another, and they can sort of coherently organize themselves to do intelligent things. In order to do that, they need communications, and the whole 5G environment is developed to try and facilitate wireless communications between millions and possibly even billions of devices. At the bottom there, you see the new Apple iPhone, or I lie, it's actually a Motorola. I think it's from the 1980s. It is the first mobile telephone. And you can see we've moved a long way since then. I think that device cost about $10,000 in current terms. And it had about, I think, half an hour of talk time. And we've progressed significantly from those times, but obviously the origins are going back to the 1980s. On the top in the center is essentially a 3D printer, a very large-scale 3D printer that can print things like cars. And that's seemingly the future that we're heading towards, large-scale manufacturing, but bespoke manufacturing. Instead of having, generic manufacturing, instead of having a production line that produces one model of automobile, you can have essentially production facilities that can produce whatever you want on demand. So everyone can have a car of their own that looks different from everyone else's car, for example. And we have the technologies, and we're heading in the directions to be able to do that. And to a large extent, that is an electrical engineering endeavor. Not the mechanical side, but the control of it and the making it possible. On the top right, you see something to do with self-driving cars. Our future is self-driving cars. They're available now, and they're certainly not going to go away. And I think we're going to move towards an environment where people don't own cars, but cars just roam around carrying people where they need to go. That seems like the logical endpoint. And at the bottom is a self-driving boat that we've developed at UCT. It's part of our endeavor to try and do this. We're trying to contribute to the scientific knowledge of the Southern Ocean and building devices and systems for basically monitoring the ocean health and otherwise. Here's another example, the square kilometer array, very high technology. A project started about 10 years ago, and it's basically a radio astronomy observatory that spans continents. The idea is on the left there you see a satellite dish, which is actually the antenna that can image in the radio spectrum. And one of the images that it produced, for example, is the image on the right, which is, it's our galactic center, as seen in the radio spectrum. And the square kilometer array, I said it's a huge device. In the end, it's going to be many, many, many of these dishes with a cumulative total area of 1 square kilometer. But I think I forget the exact numbers, but it's many thousands of dishes that essentially have to be linked together, and they need to all operate as one. And in order to do that, they need massive backhaul networks. They produce huge amounts of data, and that data needs to be processed at incredible rates. So the technological drivers for this kind of project are quite profound. And I mentioned in my introduction as well, the electricity and the renewable revolution is something that we very quickly are moving on towards. On the left-hand side, you can see something that we're quite familiar with nowadays, a city in the dark with the electricity supply has failed. And just to indicate, so certainly rolling blackouts are a feature of the environment in South Africa, but they exist everywhere else as well. In the center there, the whole, I'm not sure if you can, you can't see my mouse, but in the center on the left is a aerial photograph of the, well, I guess it's a satellite photograph of the United States of America, and there's a big hole in the top right corner. The northeast area had a blackout that essentially took out 6 states, I think 5 or 6 states and parts of Canada. And essentially it was caused by a software bug. Something happened to one of the power lines and the software didn't inform people of the right sort of things and it didn't take the right action. And it essentially caused a collapse of the entire portion of the grid. So, you know, these kinds of things do happen in other environments as well. Now, our future, I've mentioned, is renewable. We will run out of fossil fuels. So nowadays there's a huge push towards wind power, solar power, and all these other alternative energy sources. We will never run out of sunlight, or at least when we run out of sunlight, we're not going to. We'll have bigger problems to worry about. But sunlight is essentially an unlimited resource as far as we're concerned, and energy and electricity is obviously fundamental in the world of electrical engineering. Right, so aside from that, planning projects, estimating times, costs, managing and testing implementations, ensuring that the things that get built and developed are health and safety compliant and safe to use and safe to be around. Those are all very important attributes or characteristics of the engineering enterprise. And engineers, electrical and otherwise, I guess, very often work in transport. They work with lighting, heating, ventilation, power generation, distribution, renewables, quite a lot in the manufacturing and construction industries, and a whole lot of others. Where would a typical engineer work? Well, one place, for example, is in laboratories, universities, and research facilities, such as the one that I'm working in, but many others as well. If you think Amazon and Google, they all do high-level research as well. Power generation, transmission, distribution, the whole sort of infrastructural side of power production and transmission. Often in construction, factories, mines, industrials, and power production plants. So engineers essentially build factories or design factories that produce things subsequent to that. And they're obviously instrumental in formulating those technologies. Railways, aerospace, automobile industries. We're familiar with telecoms is a huge area in South Africa. We've got many telecommunications providers, and they all need lots and lots of electrical engineers, and tech innovation, gaming, and the like. And finally, I've mentioned finance, logistics, engineering services. I think I've got about 7 PhD graduates that are now working in finance with hedge funds and derivatives. So the skills that engineers have are very much in demand outside of engineering. And we find that engineers are very mobile in that respect. All right, so those are the skills. The skills that we really try and develop are problem solving, and everything else sort of follows on from that. We also want people to be pragmatic and to be able to sort of envision how to turn concepts into realities. Engineers need to be able to communicate with other people, both written and spoken. They need to be able to work with other people. The world's a complicated place, and not one person can't know everything. So team working is essential as well. And very large component of engineering is project management, and that involves planning and deploying solutions to particular problems and the like. Right, in our department we have 3 programs. Roughly speaking, electrical engineering is the power generation and distribution side of things. Mechatronics is more geared towards the bridge between electrical and mechanical. And I guess I mentioned before, it's robotics, automation, making intelligent devices that have a physical attribute corresponding to them. And electrical and computer engineering, our EC students essentially have very good background in computer science and computer programming, and producing computer hardware for particular applications. So they can design, build, and program computing systems. Right, I've mentioned that there's a show reel, so I'll just play this and then we'll move on to questions and answers. My name is Fred Nicholls. I'm the head of Department of Electrical Engineering at the University of Cape Town. UCT is a world-class university and we offer 3 programs in electrical engineering: electrical and computer, straight electrical, and a mechatronics program, which leans a little bit more towards robotics.
I'm Amir Patel. I'm an associate professor in the electrical engineering department, and I'm also the program convener for the mechatronics degree. The days of, purely mechanical or purely electrical systems are gone. So everything involves aspects of software engineering, and then also more recently things like machine learning and AI are becoming extremely prevalent and useful for many fields. Hi, my name is Yubir Gordon. I am currently doing my master's in wireless charging for drones. Renewable energy in general is just important for future generations, and it's important for the well-being of the planet as well. Using wind energy and solar energy as renewable energy sources, it can generate large amounts of power. We can use this to power households and even charge electric vehicles and electric bikes.
My name is Kuko Kushe. I'm here at UCT, studying towards a master's degree in electrical engineering. I finished my BSc in mechatronics in 2019, and I started my MSc this year. I believe over the past 4 years of my degree at UCT was honestly one of the best times of my life on an intellectual perspective, because if I wanted to build something, there was always someone who could help me, and there were resources in the university that I could utilize to actually get to that point. The biggest motivator that is important as we're actually going to sustain you is following what you're interested in, because that's what's going to last, and that's what's going to give you direction.
I'm Trevor Bourne. I'm an emeritus professor. The students are exposed to more than 100-year history of electrical engineering in ways that reflect what's happening outside in the real world. And I think that gives a lot of opportunity for learning.
In terms of the equipment, the department has everything in terms of the machines that you would need. We are given free rein to try out many ideas, and the cool part about that is I may have an idea and not know where it's going to be, but the university will facilitate how we can turn that into an innovation which will benefit society.
No, I'm very, very, very proud to be part of UCT.
Thank you for attending this presentation. We look forward to seeing you in 2021, and we wish you the best of luck in your examinations. All right, sorry, no, as I said, that was made last year, so the 2021 reference, I guess we should be saying 2023. Let me just terminate that presentation and just see if we have any questions that are coming out. We've got a question about if you're interested in virtual reality or augmented reality, should you be doing mechatronics or electrical and electronic? My guess is that something like augmented reality, virtual reality, it's almost a computer science discipline. It's rendering to a large extent rather than engineering. And so I would say our electrical and computer people are more geared towards that type of technology. Mechatronics, because they do so much, because our mechatronics students have to know quite a lot of mechanical engineering, they have relatively less exposure to basic computing, well, to advanced computing, put it that way. So all of our graduates will end up being able to program, but our electrical and computer engineering students would be able to program well, or they'd have a lot more practice at programming. Do students get engineering overalls, PPE? The answer is no, but if you choose to come in overalls, we won't tell you to go away. We do have a very strong practical component to our programs. So it's not just lectures, but typically an engineering student in the university, I speak with a bit of caution because COVID has changed things to some extent, but presumably we'll return to something more familiar as time progresses. But typically our students would attend lectures in the morning and then practicals in the afternoons. So there's a lot, that's half of your time, roughly speaking, should be involved in practicals. Much of that is done in the university, but we do occasionally manage to do site visits or tours of other facilities that are around, at least in the local neighborhood, or the local Cape Town environment. What is the difference between a BSc engineering, a B-Eng Tech, or a B-Tech? Essentially, my view is a BSc in engineering, we're trying to develop people that are almost innovators and developers in technology. So it's not quite as cut and dried as that, but a traditional university of technology would produce somebody that is more able to actually work with the devices at a very low level. You know, when I started electrical engineering and someone said, when I told people I was doing electrical engineering, the first question they used to ask me was, can you fix a television set? And the answer really is, no, I can't fix a television set if it's broken. But I could probably design and build one. So electrical engineers, BSc engineering graduates should have a much higher level view of complexity and how to turn problems into solutions. And they won't necessarily be able to do the very low level stuff that a technologist would be able to do. Sorry, this is quite a difficult forum. It's like I'm talking to myself, but it does appear that there's some people out there making questions. Is there a demand for females in the field? There's a demand for females in every field. Traditionally, engineering has, I'm not going to say it's been a hostile environment, but it has been a difficult environment for women to operate in. But I think that is changing, and it's changing quite fast. At the moment, I forget the exact numbers, but I think our electrical engineering department, about 30% are female. And we're actively working towards driving those numbers up as far as we possibly can. Is electrical and computer engineering 50-50 between the two parts, or is there more of a focus on either? The answer really is there's more of a focus on engineering. From my point of view, programming and computer software engineering are an element, or are elements that we would like our students to be conversant with. But first and foremost, we want them to have the engineering skills. So we produce engineers. Incidentally, there is a computer engineering program in computer science, which will look at it from the other side. It'll be primarily computer science, but with a little bit of engineering aspects to it. I believe Denzel asked me to keep strict time, so I believe we've run out of time here. So I think the live event will terminate round about now. Evidently, if you remain and you keep on asking questions, we'll keep on answering them until everyone leaves. So feel free to carry on asking questions, and we'll carry on answering them. Anyway, thank you for being interested in UCT, and we look forward to seeing your applications for next year. And good luck with your exams and all the rest of it. Thank you.